Okay, 3.2 is on logarithmic functions. So let's talk about what a logarithm is. Suppose you have 2 to the power of 1. We know that that's equal to 2. 2 to the power of 2 is equal to 4. And then when we jump from an exponent of 1 to 2 to 3, we get that 2 to the power of 3 is equal to 8. So in jumping exponents from 1 to 2 to 3, my values jumped from 2 to 4 to 8. Well, what if then I wanted to raise 2 to the power of something and get an answer of 6? What should the exponent be, right? So that 2 to the power of that exponent is equal to 6. That's the question that a logarithm answers. So a logarithm is just the exponent, okay? So the way we write that is, okay, what is the exponent so that 2 to the power of that exponent is 6? Well, log base 2 of 6 is what? Okay? And remember, when I have something like this, 2 to the power of 1 is equal to 2. This is called the base. Well, here too, this is called the base. So when I have 2 to the power of something is equal to 6, base 2, base 2. So same situation. All right, so anytime I'm dealing with exponents, right? So for example, 2 to the power of what will give me 8? Well, I say log base 2 of 8 is what? 3 to the power of what will give me 9? Well, I say log base 3 of 9 is what? Okay, so these two are equivalent forms. All right, so let's come over here. As you can see in what I just did over here, I can write the same question. I can pose the same question in two different ways. One is an exponential form, one is a logarithmic form, but they mean the same thing. I'm asking the same thing. So here too, the logarithmic form will look like this. Log base b of x equals y. And the exponential form will be b to the y is equal to x. So in the first case, this is asking b to the power of what is equal to x. And here, same thing, b to the power of what is equal to x. Okay? All right. Well, taking that along with us, let's look here. Let's take a look at this one. It's asking b to the power of what will give me 1. So if I have any old number, what should I raise it to get 1? Well, what a number to what exponent is always 1? 0, right? 3 to the 0 is 1. 7 to the 0 is 1. B to the 0 is 1. That means log base b of 1 is equal to 0. All right, same situation. B to the power of what gives you b? So what should the exponent be so that we get the same thing back? Well, the exponent should be 1. So log b of b is 1. Okay. Well, what about something like this? We have log base b of b to the power of x. Well, that just equals x. Okay. So what is this asking us? Well, it's telling me here I have my base b in the red. All right. What should my exponent equal to so that I end up with b to the x? Well, it should equal to x. All right. Similarly, b to the power of log b of x is equal to x, right? So just think of it as these go away and we just have x left. Okay. Well, let's use those here. All right. I want to use this property, right? So now I have log base 2 of 16. What I'm asking is 2 to the power of what gives me 16? Well, I know that 2 to the power of 4 is equal to 16, so this is 4. Okay? Now, 5 to the power of what will be 1 over 125. Okay, so to go from 5 to 125, you know that you need an exponent of 3. However, to go from a fraction, I'm sorry, to go from a whole number to a fraction, right? I'm taking the reciprocal, so there is a negative exponent involved. So 5 to the negative 3 is 1 over 125, meaning this is equal to negative 3. All right, what about this one? 3 to the power of what is equal to root 3? Okay, but what's root 3? Well, that's 3 to the half. So 3 to the power of what is 3 to the half? Well, 1/2. Okay, what about this one? 8 to the power of what will give you 5/12? Well, it turns out it's 3. And here, 22, log 22 is just 15.5. Okay? All right. Now, these are general logarithms. Well, let's talk about what we call a common logarithm. This is, so a logarithm can have any base, right? You're always looking, a logarithm as an exponent. So any number could be raised to an exponent. 2 to the 5, 3 to the 7, 5 to the 2, right? But there is one base that shows up all the time. How often do we hear 10 to the power of something? Well, this is something that shows up all the time. Everything is always times 10 to the power of something, and so on. So the base 10 is a more common base. Therefore, the logarithm with a base 10 is a more common logarithm, right? So now let's think in powers of 10, okay? 10 to the 1 is 10. 10 to the 2 is 100. 10 to the 3 is 1,000, and so on and so forth. So now, if for the first one, if I wanted to ask, what exponent of 10 will give me 10 back, how would I ask that? Well, it'll be log base 10 of 10 equals to 1, okay? Now, because this base 10 is so common, we just at some point give up writing it. So rather than writing log base 10 of 5, let's say, I will write just log of 5. And when there is no base, it's understood that there is a default 10. Just like I would never write 1 times x, right? It's just x. It's the same situation. All right. So here, I have log base 10 of 1, meaning, suppose there is a 10 there. 10 to the power of what will give me 1? Well, the answer is 0. Okay? Again, suppose there is a 10 here. 10 to the power of what will give me 10? The answer is 1. Suppose there is a 10 here. 10 to the power of what will give me 10 to the x? Well, the answer is x. All right? So we do have to understand these, but at the same time, you have to have them memorized so well that you can just rattle them off. Log of 1 is 0. Log of 10 is 1. Log 10x is x. 10 log 10x is just x. Okay? All right, so let's take a look at this one. Now I want log of 10,000. So basically this is asking 10 to the power of what is 10,000? Well, if you see here, with each exponent, you have the same number of, you have that number of zeros. Well, to get a, let's see, 1, 2, 3, 4 zeros, we need 10 to the power of 4. So this is just 4. All right, what about here? Excuse me. 10 log base 10 of 12, right, is just 12. All right, for ones like this, log of 14, I cannot mentally raise 10 to an exponent and get 14. So I have to use my calculator on that one. All right, so here's my calculator. Now I have log of 14. Here's the log button. 14. The calculator has a built-in base of 10, so you don't have to put anything. If it had a different base, then you would. So log of 14 is 1.15. And I know that the new models now make it so that you can put in any type of base as well. All right, well, what about this one? Log of negative 12. So this is asking us 10 to the power of what will give you negative 12. Is there any way to raise any number to an exponent, any positive number to an exponent, and get a negative value? Well, you can think, but I don't think you can come up with anything. So this is no solution. It's not possible, right? So log of negative 12, not possible, all right? You can never, ever, ever have a log of a negative number because you can never take a positive base, raise it to an exponent, and get a negative value. All right, so we talked about common logarithms. Well, what about natural logarithms? A natural logarithm is a logarithm with base e, right? So it's log of e. But instead of writing log e, log e, log e, right? So instead of writing log e of x, it shows up so often that I just call it ln of x. So another Jeopardy trivia fact, ln is natural logarithm in French, right? It'll be logarithme naturel. That's why it's ln, okay, natural log. So ln is just log e of x, right? If you really want to mess with some people, instead of ln of x, you could write log e of x. You're saying the same thing. You're just not going to have too many friends left. Okay. So same situation. ln of 1 is 0, right? Remember, this is log base e. So e to the what gives you 1? Well, 0. Remember, this is here. This is log base e. So e to the what gives you e? 1, right? ln of e is 1. You're walking down the street, somebody taps you on the shoulder and asks, hey, what's ln of e? Well, it's 1, okay? ln of e to the power of x is x. E to the ln of x is x, all right? So here, these are the most fun problems you're going to solve. So ln of e is 4.5. They all go away. So the answer is just 4.5. All right, what about this one? ln of negative 2. Remember, you can never take log of a negative number because you can't raise anything to a power and get a negative number. So this is not possible. E to the ln of 4, just 4. ln of 7, for that we need to turn to our calculators. ln of 7, 1.95. We actually go to 3 decimal places, so let's put in 3 decimal places. I should have done the same for the other log. All right, so let's talk about graphs of logarithmic functions. So if 3 to the power of 2 is equal to 9, and if I write this as log base 3 of 9 is equal to 2, these two are inverses of each other, all right? And we've talked about a function and its inverse, and we've said that a function and its inverse, when graphed, are symmetric along the line y equals x. So if I were to draw the line y equals x here, now if I were to draw e to the x, or anything to the power of x, it would look like that, right? So do you see how b to the x and log b of x are inverses of each other, all right? Which means the domain and range are switched. So whereas an exponential function has a domain of all reals, the range of a logarithmic function is all reals. And whereas the range for an exponential function is 0 to infinity, it's the domain for this one. Okay? Now, for the exponential function, we have a y-intercept of 1. For the logarithmic function, I have an x-intercept of 1. For an exponential function, the x-axis is the asymptote. For a logarithmic function, it's the y-axis. Now, let's talk about end behavior. All right. We can definitely talk about what happens to this function as x approaches positive infinity, right? As x approaches positive infinity, f of x keeps going further and further up, like here. Now, we can't, however, we cannot talk about what happens as x approaches negative infinity because this thing stops right there, right? So the best we could do is what happens, right? What's the farthest left this goes? Well, it's this vertical line, right? X equals 0. So the best I could do is what happens as x approaches 0 from the positive side. And as x approaches 0 from the positive side, my graph goes down to negative infinity. All right, so let's graph one. What we're going to do is we're going to graph log base 2 of x. And I know that now the y-axis is the asymptote, so it's x equals 0. Now, to do this, okay, yeah, we're going to pick points, but we're not going to pick points in the traditional style of how we used to pick points. What we're going to do is we're going to analyze the exponents of 2. So what are the exponents of 2? Okay, what do I know? What are the powers of 2? Well, I know that 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. Okay, what about on the other end? What's 2 to the power of 0? 1. What's 2 to the power of minus 1? 1/2. What's 2 to the power of minus 2? 1/4, right? So if next time when you're walking down the street, you could just keep saying this to yourself, all right? You could do it with the 3's. 3 to the power of negative 2, 1/9. 3 to the power of minus 1, 1/3. 3 to the power of 0, 1, right? 3 squared, 9. 3 cubed, 27. So you could just rattle off the powers of, let's go back to 2. We could rattle off the powers of 2. 1/4, 1/2, 1, 2, 4, 8, 16, right? So basically, these are all the numbers that you can get by raising 2 to an exponent. So now, remember that if this is a logarithmic function, then the answer, or y, is the exponent, right? So your y's are going to be all the exponents of 2, right? So I have an exponent of negative 1, of 0, of 1, of 2, of 3, right? And if my exponent is negative 1, 2 to the minus 1 is half. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared, 2 cubed, and so on. And now, let's do this. Here I have an asymptote. When x is 1/2, y is minus 1. When x is 1, y is 0. When x is 2, when x is 4, it's 2. And when x is 8, it's 3. 1, 2, 3. And look, guys, look at that. Logarithm. Logarithm. There you go. Okay? So what's the domain? Not all reals anymore. No, it goes from the asymptote out. The range, though, is all reals. The x-intercept is 1. Now, end behavior. As x approaches 0 from the positive side, so as x's are going that way, what's happening to the graph? Going down, plummeting into negative infinity. And as x is approaching positive infinity, I'm going up. Where is it continuous? Everywhere on its domain. Okay? Alrighty. So let's do another one. 1/3. So now what I want, okay, now what I want are the powers of 1/3, okay? So 1/3 to the power of negative 2 is 9. 1/3 to the power of negative 1 is 3. 1/3 to the 0, 1. 1/3 to the 1, 1/3 squared, okay? So when x is 9, y is negative 2. When x is 3, y is negative 1. When x is 1, y is 0. When x is a third, y is 1. When x is a ninth, there we go. What's my asymptote? the y-axis, of course. And now, gotta follow the asymptote. Got to follow the asymptote. There you have it. So look, this is an example of exponential decay, right? Because it would have been, I'm sorry, this is an example of logarithmic decay because it would have been exponential decay. So x equals 0 is my asymptote. Domain is 0 to infinity. Range is all real numbers. X-intercept is 1 and 0. Now, as I approach 0 from the positive side, this time I'm going to positive infinity. And as x approaches infinity, I'm going to negative infinity. And it's continuous everywhere on its domain. All right. Now, let's do this one, the case of the ln. Now, what's happening here? Excuse me. It's ln of x minus 6, right? So there is a shift 6 units to the right. So where is my asymptote now? It's here, right? It's at x equals negative 6, all right? So in this case, I'm going to be raising e to the power of negative 2, negative 1, 0, and so on. And since it's e, we're going to go ahead and use our calculators. So here, it's going to be ln of x minus 6. So let's see what we're going to do here. All right, so as I was turning on my calculator, I also realized that this is supposed to be positive 6, right? I put it in the right place, but okay. So basically, these are going to be the exponents again. And again, my base is e, right? So I'm going to do e to the negative 2. So let's do e to the negative 2. I get 0.1, but remember, everything is shifted to the right. So I do 0.1 plus 6, 6.1. Okay, now e to the minus 1 is 0.4 plus 6, 6.4, because I'm now manually shifting everything. E to the 0 is 1, plus 6 is this. E to the 1 is 2.7, plus 6 is 8.7. E squared, we said, was 7.4, plus 6, 13.4. Okay, so at 6.1, we're at negative 2, right about there. And then we're at negative 1 when it's 6.4. And then at 7, we're at 0. At 8.7, we're at 1. And that's about all. So there we go. That's how it looks. Okay. So the domain is 6 to infinity. So it's always asymptote to infinity. Range is all reals. X-intercept is 7. And behavior is as x approaches 6 from the positive side, and it goes to negative infinity. As x approaches infinity, it goes to positive infinity, and it's continuous everywhere on its domain. All right, so now, the intensity level of a sound measured in decibels can be modeled by this equation. So this is the intensity level of a sound. This is one example where we measure things in logarithms. So W is the intensity of the sound, and W naught is just a constant. Now, if the intensity of sound of a person talking loudly is this, so if you're talking loudly, this is your intensity. What is the intensity level of the sound in decibels? So if the intensity level of a sound of a person talking loudly is this, what is the intensity level of the sound? So here, this is your W, and this is your D of W. Okay, so let's see what D of W is. It's 10 log W over W naught, 1 times 10 to the power of negative 12, right? And so now at this point, what we're going to do is we're going to plug this into our calculator. And so dW is equal to 45 decibels, which you could also write as 45 dB. Okay? So we plug it in the calculator as is, just put parentheses around these, right? So it's 10 log this divided by that. Now, if the threshold of a certain person with a hearing loss is 5 decibels, will a sound with an intensity level of this be audible for that person? Okay? So if this is the intensity level, what should it be? So again, this is W. So let's see what D of W is going to be here. So it's 10 log 2.1 times 10 to the negative 12 over 1.0 times 10 to the negative 12, right? And look what happens here. When it's 10 to the negative 12 and 10 to the negative 12, you can just cancel them out. So it'll be D of W equals 10 log 2.1 over 1, which is just 2.1, and you can plug it in your calculator that way. And the answer will be 3.22 decibels. So if this is the intensity level, this person is not going to hear because his threshold is 5. So no, he can't hear, or she. All right. Sound in excess of 85 decibels can cause hearing damage. Okay, so all you people with your earphones, determine the intensity of sound that has an intensity level of 85 decibels. Okay, so what we're going to do is this. On the one hand, we have our intensity level, right, which is 10 log W over 1 times 10 to the negative 12. Okay, now we want to know what W should be so that this whole thing equals 85. Okay, so what are we going to do? Well, we're going to graph it, and we're going to use our graphing calculators to our advantage. So in Y1, I'm going to plug in 10 log W over 1 times 10 to the negative 12. And in Y2, I'm going to put in 85, and I'm going to see where these two are going to intersect. All right, so here's my calculator, right? So what I did is 10 log x over 10 to the power of negative 12, since it's a 1. And in Y2, I'm going to put in 85. Now, I need to adjust my windows because look, these numbers are like 1 times 10 to the negative 12, right? So I need to be really, really tiny. So I go to my window and I'm going to make it really, really tiny. So I'm going to go from 0 because it can't be negative. So, okay, so X is my W, which is the intensity level, and it's going to go from 0 to 0.0001, right? So hopefully that'll work. Now, how do you know? You're going to have to do some trial and error. And actually, I'm thinking this might be a little too small. Let's do 0.001. Okay? And for the Y, right, look, Y2 is 85, right? So I need the Y to be bigger in order for me to be able to see Y equals 85. So why don't we go from 0 to, I don't know, 100. Okay, let's graph this and see what it looks like. Okay, so there's the first one, and there's the second one. Okay, and now what I want to do is I want to see where these two intersect. So I'm going to do second calc, intersect. Now it asks, is this your first curve? Well, yeah, y equals 10 log blah, blah, blah. Yes, that's my first curve. Is this your second curve? Y2 equals 85? Sure is. Do you want me to guess? Knock yourself out. Press enter. So I have that it's 3.2 times 10 to the power of negative 4, right? So W is equal to 3.2 times 10 to the power of negative 4 watts per square meter. So that's the answer. Okay? All right, now, what I had said to a couple of people was I would give you some suggested problems for you to start on your homework before you come to class. These are completely optional, so if you want to start, you're more than welcome to. Although these are very, very quick, right? So why don't you go ahead and do, let's say, number 5, number 15, number 43, and number 74. Okay? All right, I'll see you in class, everybody. Bye-bye.